because who wants to sit through Mr. Resnick talking for an hour and a half?
I mean,
An inflated balloon. I'm going to do something strange. I'm going to do problem number B first. Okay? I'm going to do B11 first. So I've got right here, I've got a balloon. I've got positive charge distributed on the outside of the balloon. Agreed? I am going, and that balloon is a sphere, right? Okay, and I've got 8 microcoulombs distributed on the outside. I have, is the 0.14 meters is my radius, or diameter. It's the radius. Okay, good. Okay, so that says I want to find the electric field intensity at a distance 14.1. Again, I'm doing B first, right? So 14.1. So out here at 14.1, I want it, sorry, 0.141 meters, because we're changing it to meters. I want to electric field at that spot. Now, Karis.
Yes.
What shape do I draw? What would be symmetric around a sphere? Perfect. Let's draw a sphere.
Okay.
So I'm going to draw a sphere around the outside. Now I have to have it so the electric field is the same at all points. So that sphere has to be all 14.1 everywhere.
Okay.
Now, the first point you get from AP Central, and it's the dumb point. So one of the few places where the physics people have dumb points. Unlike calculus, where the whole test is full of dumb points. This one, you need to have it. Gauss's law. Q enclosed over E naught equals the integral closed E dot dA. That has to be written down. It's usually 1 point, and you have to write it down. Now, they will sometimes let you get around that by showing you know it. Sometimes they won't, because depending on the context of the question. So you don't know when they're going to do what, so you're going to write that down the first thing you do is see a sphere, and you're going to write an electric field outside. Write that down. That's 1 point. You don't have to think. Just write it down. Now, the next step is always going to be making this EA. Before you do that, though, you need to check some things. One, this circle right here. That circle right there means I completely enclose it. Did I, in fact, completely enclose it? Okay. Number 2, is every single electric field line going perpendicular to the surface I drew? Notice you're going straight out. Yes, so I took care of the dot, too. Last but not least, is the electric field the same everywhere on the outside of this thing? Is it same? Then I can then write this as EA, Q enclosed, and this is what we're always going to do, because the answer to that is no on any of those. You can't do the problem. You don't have the math.
Okay.
So as silly as it sounds, you're going to want to write this down every single time to get the point.
Okay.
Then after that, this is going to be the next step. And after a while, you're going to forget what we're discussing that gets you from here to here. Okay? I want you to remember it. I'm going to repeat it often, because sometimes they'll say, well, if you move the charge a little bit to the right, what happens? Not, give me a number. What happens? You know, what if the shape we drew had a hole in it? What does that mean? What would happen to our flux? It would be less, because I'm not capturing all of it. You know, that sort of thing. And so I want you to understand those ideas, because they can ask them.
Okay.
But to be truthful, once you start doing Gauss problems, you're at this step, and then you're going to write this step next time every time, because you drew a perfect symmetric shape, and everything's good, because you get to choose a shape. Okay, so Q enclosed. How much charge did I enclose? 8 times 10 to the negative 6 over, what's E naught? With me, Karis? And then what's my electric field?
That's what we're looking for.
What we're looking for? What is the area of a sphere of 14.1, the one we drew? 4 pi r squared, where r is going to be? Where r is going to be what, Karis?
R is going to be 0.141.
0.141, the shape I drew. Again, it seems weird, but the shape I drew is what the electric field is going to be at that point, so that's why we drew it that big.
Okay.
So it's not something arbitrary. Okay, put it all in my calculator, hit equals, and I get an answer for my electric field there. And notice what we're getting away from. I'm not summing as I integrate around the outside of the sphere all the different DQs. That's why we like this. Could you do it that way? Yes. Would your hair fall out and be suspect to all sorts of pain and suffering? Yes. which is why we do it this way. 8 exponent. Somebody check my math because it's going to go badly. I can tell already. I'm having one of those mornings. 8.85 exponent negative 12 divided by 4 divided by shift pi divided by 0.141 squared, and I get a really large number. What do you get for electric field? I get 3.62 times 10 to the 6th newtons per meter. Is that right? Nice. I got one right today. Good, Karis?
Yes.
Okay, let's do the second piece of the problem. The second piece of the problem, I'm asking, what would happen if I do 0.13 meters? What would be weird about that problem?
It's already inside.
It's inside. So this is a piece that people always have trouble with, and I notice people are talking, which just scares the heck out of me. What's the charge enclosed, Karis?
8 times 10 to the 6, negative 6.
Look at my picture. What's the charge enclosed?
Oh, 0. It's
0. What's my electric field inside of that balloon? 0. Because that charge is distributed on the outside of that balloon, there would be no electric field in there. Now, why does that make any sense? Whoa, 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 whoa. I got positive charge all over the place. There would be electric field in there, wouldn't there? Think about it. If I'm over here, what are most of the charges doing? They're all over here pushing that way. The ones that are closer are pushing the other way. Guess what it balanced out to? 0. There is no electric field inside. So this equivalent being between two charged particles would be right in the middle. No matter where you are, symmetrically, you're always going to be close enough to one of those walls that these are pushing harder, but there's more of them over here pushing the other way.
So if you put an electric, or if you put a charged particle inside of this balloon, it just stays in the balloon?
Stay right where it is. Wherever you put it, stays there. No electric field. Okay? So that's huge. Now, I'm going to go ahead and let you make sure you can do it. So try C right now. Again, I do apologize for saying do your homework, but do it again. But try the letter C right now. And we'll deal with that. Nothing, we're doing something silly. So I'm going to start off with the same place I always start off with. I'm going to start off with, I'm going to do Q enclosed over E naught equals the closed integral E dot dA. It's always going to become this. Unless something really weird is going on, I drew a bad shape. So now it's Q enclosed, which is 8 times 10 to the negative 6. E naught is 8.85 times 10 to the negative 12. The electric field, what I'm looking for, the area is going to be 4 pi, what is the radius of the shape I drew? 0.5 squared. And so if you've got that down, then it's just a matter of putting buttons in your calculator. Okay. Okay.
287,537.
Still no?
Still no.
All right, let's do some work.
170. I got 177,000.
All right, so we're going to do 8 exponent negative 6 divided by 8.85 exponent negative 12. So I get 903,000-ish. Divided by 4. Divided by pi. Divided by 0.5 squared. I'm getting 287. 288,000 units per kilo. Careful with your parentheses, I imagine. Are you dividing by 4 pi any chance? No, that wouldn't do the problem. The heck would it be? Yeah, I don't know what that number is weird. Feels like I got 0.5 squared wrong or something.
177,000.
I don't know how to. Feels like you got like an 8 or a 7. One of these numbers is wrong. You got 0.5 over there squared? That's the one I care about. 4 pi?
Okay, I did it again. Now I got it.
Okay, all right. That should work. Okay, everybody try 12 now. Try 12. 12 is going to be different.
I don't